Good morning, everyone. It's Tuesday morning at 10 a.m. in Switzerland, and our Space Café special 33 minutes with Michael Kueppers will begin in a few seconds. Thank you, by the way, for joining this exciting interview on this special day, because you guys know what day it is. It's Asteroid Day, and Asteroid Day is all about commemorating the legendary Tunguska event in Siberia on June 30 in 1908. So why Asteroid Day? Asteroid Day aims at raising awareness about asteroids and what can be done to protect Earth and future generations, of course, from a catastrophic event. And we did have a bunch of close calls in the past couple of years. For example, in 2014, asteroid was discovered, and that asteroid went past in a very close distance of 1.25 million kilometers from Earth the same year. And then there was another one. Just a couple of days after it was discovered, it passed the Earth in a very, very close distance of 490,000 kilometers. So I would say that are two very close calls. And as always, guys, thank you so much. We really appreciate you being here and your participation. Who am I? I'm Markus Moslechner, the guy with the unpronounceable Austrian last name, and your host. I'm director and science journalist at Terramata Factual Studios and the host of Space Café podcast, which I highly recommend checking out for you guys. SpaceWatch.Global is a Swiss-based online platform for information in and about space and new space activities in a geopolitical context. But most of you know that already, I guess. So now let's go to the heart of the matter, the heart of the show today. Today, I'm super honored to be joined by a super and very special guest, Dr. Michael Kueppers. So when would you go to Michael? When you're interested, for example, in the composition and structure of comets, when you want to learn about surface properties of asteroids and comets, or when you want to know more about solar system formation. Michael is a planetary scientist at ESA and mission scientist for the Hera project. He was with the Rosetta mission, and you guys, I'm sure you remember that spectacular landing on the comet Gerasimenko, right? And this is Michael's mission. He will tell us a lot more about that in the course of this webinar. And I'm super proud now to welcome Michael today. He's with that mission that ESA calls the Planetary Defense Mission. How it cannot get more spectacular than that. Welcome, Michael.
Hello, good morning. Thanks for the introduction.
Of course, of course. Michael, to cut right to the chase, do we have any imminent asteroid, meteor, or comet danger heading for Earth?
Fortunately, no, or none we would know of. So we are.
that's the bad thing about it, right?
Yes. I mean, we are observing or we are detecting more and more asteroids, but of course we do not yet know all of them. But those that we do know pose no danger in the near future.
Okay. Before we go into detail, because people keep mixing a bunch of terminologies up with one another. So what's the difference between asteroids, meteors, and comets?
Okay, I start with asteroids and comets. Both are really old. Both are leftovers of the times when the solar system formed. And the general idea is that asteroids were closer to the sun, where it was warmer. So any ice that may have been there evaporated, and they are made of stone or metal, while comets are from further out. And they are a mixture of ice and dust, and that's the reason when a comet gets close to the sun, that then the ice starts to evaporate and we see those spectacular coma and tail of the comet.
Wow. And there's a fascinating theory out there that the water we have on Earth, all the bodies of water together, could have originated in comet bombardments back in the day. Is that right? Is that still a valid scientific theory?
That's the scientific theory, and the basic idea is a little bit similar. Earth formed relatively close to the sun, and Earth formed, as all the planets, through slow hierarchical agglomeration, which means one starts with dust. The dust accumulates to small bodies, essentially small bodies like the comets and asteroids that we see now, and they have collided further and have created the planets.
Fascinating, fascinating.
And
I mean,
because
yes?
Earth was close to the sun, the water shouldn't have survived, and therefore one maybe nowadays leading theory is that comets and asteroids have brought the water in.
Very interesting. I mean, like, it's still so fascinating to me as a science journalist and as a layperson to remind oneself of the fact that 2/3 of our planet are made out of water, and we have essentially no idea where it comes from. There are a bunch, as you mentioned, of theories, but we do not, in fact, know where it really came from. Isn't that fascinating?
Yeah, that's absolutely true. There are, of course, different theories, but we do not really know for sure where the water comes from.
So there's a lot still to discover on Earth.
Absolutely, absolutely.
Beautiful. So I already mentioned, Michael, the Rosetta mission, to go a little bit back in time before we move to the planetary defense strategy you're working on. Let's talk about the Rosetta mission. That was a spectacular feat done by ESA a couple of years ago when ESA attempted to land a robotic probe on a comet. Could you tell us that story in a nutshell, so we get reminded about what this was all about?
Yeah, Rosetta was the first mission to rendezvous with the comet, so not just to fly by, but to really accompany the comet on a large part of its orbit around the sun.
By the way, this is the comet, right? This is
the comet, right? And I also.
How big is it?
Also the comet, something more to touch also. And yes, here we can see this image was taken relatively close to perihelion, to the point closest to the sun. And all the stuff that you see coming out is the dust that is leaving the comet. So what happens there is that the ice at or close to the surface sublimates because it gets warm when it gets in, and you see the dust that is taken away by the gas. The dust that is taken away by the gas and leaves the comet into space.
Michael, how big is this piece of rock?
It's around 4 kilometers in diameter.
Okay, interesting. And how far away? Was it back then during the encounter?
When it was encountered, it was a couple of 100 million kilometers away.
A couple of 100 million?
Yes.
Okay, so I mean, like, isn't that crazy? So someone has the idea, why not visit a 4-kilometer sized piece of rock in space, and then the other person, the engineer, asks you, how far away is it? And you tell him a couple of 100 million kilometers away. Can you make that? I mean, like, this is almost close to impossible, right?
Yeah, I mean, it's a lot of calculations behind it, and it has taken 10 years to get there.
10 years to flying time.
Yes, because
Wow.
Rosetta didn't only have to get there; it had to get there and be at the same trajectory of the comet around the sun and at the same velocity.
Wow. Velocity meaning how fast was that?
Well, the comet was at that time relatively far from the sun, so the velocity is maybe 10 kilometers per second.
That is, can you give us a number in kilometers per hour?
Yeah, it's 36,000 kilometers per hour.
Okay, this is almost as if I try to land something on a bullet shot from a gun, but the bullet shot from a gun is the 10th, a fraction of that speed, right?
Yes, Yes, yes. I mean, it was, and the way it was done is the Rosetta flew by 3 times the Earth and 1 time Mars, which also means the last Earth flyby was 6 years after launch. So 6 years after launch, you could think back to the beginning. But each of those flybys of the planets gave it substantial acceleration to get it in tune with the orbit of the comet. And another aspect of this is Rosetta. When Rosetta was launched, more than half of the mass of the spacecraft was fuel, again, to get it really in tune with the comet orbit.
Very interesting. It's almost like some of the electric cars these days carrying most of their weight in batteries. But this is a different story. So let's take a look at the precious cargo Rosetta carried to the comet, to Gerasimenko. We do have a nice image you provided, and that's the next slide, please. It's the little lander called Philae. And there's 3 very exciting images. And I don't know if you can see it. I almost have goosebumps. No, it's not almost. I do have goosebumps when I take a look at those images because they carry such a great story. Michael, what's the story about those images?
Okay, I start with the image to the upper right. So what we see here is the final landing, location of Philae, which is about a kilometer away from where it was intended to land. Okay. So what happened is, after Rosetta had arrived at the comet, it had been orbiting for a couple of months. It was a ideally safe place for the lander was selected. The lander was released from Rosetta, and it landed pretty much spot on where it was supposed to land, but due to the failure of some systems on Philae itself, instead of staying there, it bounced back, and it ended up in the location we are seeing here. So on the upper right gives the context of the whole comet where it was. The left image on the left is the detection image, and an enlargement you can see in the red box. This is where Philae ended up. Wow. So it was really, it really hit a wall and kept stuck at this wall.
Wow. And is it still there?
As far as we can tell, it is still there.
I mean, like, isn't that the most heartbreaking story ever? That this little Philae lander with his tiny circuits and tiny whatever things it's got on board to measure its environment is still sitting there, but perhaps dead because there's no battery, no fuel around anymore. So how does a scientist feel about something like this? Do you have any feelings for Philae, or are you a scientist and say, no, there's no feelings in my world?
Yeah, it was a really exciting story. Once actually this detection was nearly 2 years afterwards. So we did not know where exactly Philae was, but the region was known, and from the illumination profile, it was known that it was a overall dark and cold area. So Philae had a battery to operate 3 days, and after that, it needed sunlight to operate.
Right.
So there it was, of course, then the reaction was to try to put as many measurements as possible in the first 3 days, because as expected, afterwards it became too cold. And we then had to wait as the comet moved closer to the sun for it to warm up, with the hope that Philae could be reactivated.
Sure.
And indeed, in the next summer, by coincidence, it was summer on Earth, but more importantly, also summer on the comet when it reached perihelion. A signal was received from Philae for some time. Some data that gave some idea how it went with him, what he suffered in terms of temperatures were received. Unfortunately, we were not able anymore to reactivate for scientific measurements. The contact broke up, and we don't know for sure, but we think that probably the communication system from philae got damaged due to the harsh conditions.
Okay.
So in that sense, indeed, it is dead, if you will.
Okay. Okay. What a heartbreaking story. By the way, guys, who have just joined us recently, we are speaking today with Dr. Michael Kueppers from ESA, the European Space Agency. And we just talked about the spectacular Rosetta mission, and Michael was part of that mission. And you guys out there are very welcome to ask your questions. Please do take the time. We have 15 minutes more left to answer your questions. But before we do so, Michael, let's take a look at the next slide, please, because the next slide tells us very nicely where the comet is right now and where Philae, our little baby robot, is at the moment right now. Can you tell us where we are at the moment?
Yeah, so the red ellipse on this plot is the orbit of the comet. And it's together with some images taken from Earth at the different orbit positions. As you can see, the perihelion, the closest distance from the sun is somewhere between Earth and Mars. And the comet moves to this farthest point, to the aphelion, out somewhat beyond the orbit of Jupiter. Mm-hmm. It's now again on its inward path, a little bit behind the position where it was in March 2008. So it's now again approaching the sun and will have its next perihelion in early 2022. So this is the next return of the comet to the inner solar system after the Rosetta mission.
So you could, in fact, or do another encounter with the comet to refuel or change the batteries for Philae. Okay, that was just a joke here. So, Michael, you are currently part of the Hera mission, and the Hera mission is all about dealing with deflecting on or incoming asteroids or comets or meteors. So can you tell us a little bit about that mission and the cooperation with NASA?
Yes. So occasionally there are many asteroids in the space close to the Earth in the solar system. We currently know around 20,000.
20,000 asteroids at the moment.
Sorry?
In 20,000 asteroids 20, in proximity.
20,000 near-Earth asteroids are more known at the moment.
Okay.
And occasionally one of those asteroids hits the Earth. This can be a huge catastrophe, as it happened a very long time ago, like 65 million years, where we think that the impact of a big asteroid was the reason for the dinosaurs to become extinct. Mm-hmm. Something like this is a very rare event, but smaller ones happen much more frequently. The last remarkable one happened just 7 years ago in 2013, when a small, maybe 20-meter asteroid exploded in the atmosphere close to the Russian town of Chelyabinsk, and around 1,500 people are hurt.
But you mentioned it's a very rare event, but from a statistical perspective, it's an event that will happen. The question is just when.
Absolutely. And the rareness depends very much on the size of the asteroid. So the biggest ones were indeed a threat for our civilization, but they are very rare and unlikely to happen in the near future. Smaller ones that are also already significant will happen much more frequently. But the good news is we now think we can do something about it. And here are the missions that are trying to demonstrate the technology. So what we are trying to do is to deflect an asteroid with the idea, if needed, and an asteroid is heading towards Earth, that we could impact it and change its trajectory just enough to miss Earth. And to demonstrate the technology for that, we are going to change the orbit of an asteroid moon around the main asteroid. This is depicted here. One sees the NASA mission DART which will actually be launched next year. And then in 2022, it's supposed to hit Dimorphos, which is the name of the moon of the asteroid Didymos. It will change.
I didn't know. I'm sorry.
Sorry, I'm talking.
So asteroids do have moons. That is new to me.
Yes, for the nearest asteroids, about 15% of them do have moons.
Oh,
so it's not that uncommon for asteroids to have moons. Yes.
Okay. Good. Okay. So what's the role of ESA in this mission?
Yeah. Once this has happened, ESA is going to launch the Hera mission in 2024. It will arrive at the asteroid in 2027 and essentially look at what happened. The change of the orbital period itself one can observe from Earth, but another spacecraft is needed to look at the crater and also to characterize the asteroids, to be able to really understand what happened, how efficient the impact is, how efficient the momentum transfer from that to the asteroid is, to be able to scale this experiment to the real thing, should we really have the need to deflect an asteroid in the future.
Mm-hmm. Mm-hmm. We do have a question that fits nicely into our discussion here from one of our viewers, and George wants to know. He writes, most of the Earth's surface is water. Is it possible to calculate the impact area to react accordingly in respect to urban areas, open water areas, deserts? So is there a chance to calculate the impact area?
Yes, but normally the uncertainties are so that the impact area will be only known relatively late before the impact.
Okay. So it will be known when it's too late already. So is it better if worst comes to worst, is it better that it falls onto water or onto solid ground?
I don't know. I mean, it's definitely preferable to fall on water than to fall on a town.
Yes, yeah. Thank you.
Now, if I have to compare water with a desert, I'm not sure. Depends maybe also of the size of the asteroid, because if it falls on the water, there's no one around, but it may create a huge tsunami, which can also create great damage. So I find it difficult to answer that in one direction or the other.
Okay. Mm-hmm. Thank you. So, you told us a little bit of detail about the Hera mission. So once we know if it works the way it's supposed to work, so that the moon of the asteroid was successfully deflected, what will the next steps be then?
So the next steps in the ESA program or in the ESA roadmap are to investigate a substantial number of asteroids to understand what may expect us and what we think would happen depending on asteroid type. And this exploration of a large number, we hope, will become possible due to the advent of CubeSats. Already in DART and Hera, we will for the first time demonstrate measurements with CubeSats around such small bodies. Mm-hmm. So CubeSats are small satellites made of boxes 10 times 10 times 10 centimeters. And if at the point where those CubeSats are autonomous and can go as independent missions to small asteroids, this will dramatically decrease the cost and allow us to investigate many of them. Mm-hmm. This is the next step. And a bit further in the future would be another step to make a predictive impact, which means right now for the DART impact, we say, well, it will change the orbit period of the asteroid maybe by 10 minutes, but we really don't know. It could be 3 times more and 3 times less. In that case, based on the experience with DART and the properties of the asteroid, we would want to predict what the change in trajectory is to really be able to have a controlled reaction should we need to get rid of an asteroid that is threatening to impact Earth.
Michael, One last question to you before we move on to answering our viewers' question. By the way, thank you guys for bringing your questions in. Michael, Hollywood keeps showing us visions and imagery from nuclear weapons deflecting asteroids. Is that an option, or is that just wishful thinking from filmmakers?
Actually, it is.
Wishful thinking or an option?
Sorry, it is a real option.
Wow.
I mean, what I now described is called the kinetic impactor. And of course, because the asteroid will generally much more massive than whatever hits it, it is only a small change in the direction of the asteroid, in the motion of the asteroid, and it has to be done relatively early to be efficient. Should we have less warning time, the only option would probably be a nuclear explosion. Now, when I say nuclear explosion, it doesn't mean blasting the asteroid. That would be way too uncontrolled. It would be a nuclear explosion close to the asteroid, and the asteroid would be pushed away by the shockwave of the explosion.
Okay. Michael, let's make a quick round of Q&A, as short as possible. Brel wants to know, can asteroids bring harm to spacecraft orbiting the Earth?
In theory, yes, but it's very unlikely.
Okay. Then George wants to know, isn't a nuclear burn more preferable than an explosion?
Nuclear burns refers at the asteroid, or?
I think when we talked about the nuclear option.
Yeah. Well, what we are doing here is in that case is not so much an explosion. It's simply the satellite hitting the asteroid.
Okay.
And it will push it away. Okay, it will also create a crater, but it's not an explosive device. And in that sense, if we have the choice, I would consider the nuclear option much risky, also because of the need to essentially launch a nuclear weapon.
Okay, good. Then Shivam wants to know, where did the asteroids come from in the solar system?
So nowadays, most of the asteroids are located between Mars and Jupiter. And due to certain instabilities, some of them are then deflected into near-Earth space.
Okay. Good. Heat Yoshi wants to know, what kind of information can one get from cores of asteroids?
From the orbit?
From the cores. The asteroid core.
From the cores, I'm sorry.
Yes.
Well, it gives us a lot of information about the formation and the evolution of those objects. For example, if we investigate the interior, and we will actually do this for the first time with Hera, or try this with a radar on the tubes that we are taking there, you can test formation models like that the smaller asteroids are the products of collisions of larger ones, of collisions that they destroyed them and reaccumulate. And if this is correct, we have them made of many blocks, many very porous and very weak. And those are theories that can be tested if we investigate the interior.
Good, thank you. Rita wants to know, will there be any studies of the chemical composition of the asteroid or of the dust coming off from the impact?
Of the dust will be difficult because when Hera arrives, the dust will be gone. Of the asteroid, yes, also the mission is for planetary defense. So this is not the prime objective. There will be a spectrometer that will analyze the spectrum, which gives also some idea of the composition and also which meteorite we have on Earth may correspond to the asteroid.
Okay, good. Now, one more, that's a very interesting one. Is there any danger from potential asteroid mining projects by changing their trajectories?
That's of course for the further future now. I would say it depends It depends. It depends on the method that will be used for asteroid mining. I would expect that most of them don't change the trajectories much, so I would not expect this to be a very likely threat, let's say.
Okay. So here's two more questions. Thank you, guys. This is super exciting, the questions you're bringing in. One question to my dear little Philae baby robot. As you said, the battery died. Couldn't we use some other form of energy to keep it alive, like solar energy or heat energy of the comet? I mean, like, I think you answered the solar energy already. But is there a possibility to use different forms of energy in the future?
I mean, in principle, one could consider using essentially nuclear energy, radiogenic devices to heat the landers, and those things are indeed foreseen for NASA missions, but ESA, by its constitution, does not use them.
Okay. Good. 2 more minutes. So please, quick answers. Some people say the first life forms may have come with meteorites to Earth. So if so, what could be the evidence, or is it possible for any life form to enter the atmosphere? That's an interesting question.
So what we think today, it's not so much that life was brought to us, it's more that some of the materials like the water and some organic molecules may have come from outside and have then formed life on Earth. Okay. And those molecules we indeed see, especially we have found in comet 67P with Rosetta.
Okay. Good. So, and one last question, asteroid mining for resources. What is asteroid mining for? To bring the resources back to Earth or for manufacturing in space?
I think there's a little bit been a shift in recent years. The original idea was to bring valuable metals back to Earth, but nowadays there are serious doubts if this would be ever
feasible,
useful economically, and now the focus is more on in-space production and in-space utilization of the mining resources in asteroids.
Great. Thank you so much, Dr. Michael Kueppers from ESA, scientist at the Hera mission and scientist with the Rosetta mission, both fascinating missions. And ESA is on its way to becoming a real big global player, because ESA has a bunch of very interesting projects scheduled for the next couple of years. So please stay tuned. There's everything about those missions will be happening somewhere here at SpaceWatch.Global. Back to you, Torsten.
Yeah, thank you. Exciting talk. Thank you, Michael. Thank you, Markus. So later today, I mean, as it's Asteroid Day, we have some more events lined up for you today. At 4 p.m., Dr. Bled Bone will be my guest to chat about his new book, War in Space, Strategy, Superpowers, and Geopolitics. Then at 7 p.m., a very special event, we will facilitate the Serbian Case for Space event on how to start your career in the space industry in the Western Balkan, moderated by the team of Anja Pekulic and her colleague. This event will be in Serbian language for all of you that are capable to speak so. So next slide, please. And on our next regular web talks on the 7th of July, I'm hosting Sebastian Moranta from ESPI on COVID-19 and the effects for the European space industry. On 14th of July, Jenny Tapio, the space specialist from the Finnish government, will talk with me about the implementation of national space law for Finland and beyond. That's very exciting. And as in our first sent announcement, I'm very happy that on the 21st of July, our Niklas Hetman, Chief of the Committee Policy and Legal Affairs section of the United Nations Office for Outer Space Affairs, will be my guest and talk with me about the new frontier and space multilateralism. All events are online on Eventbrite. And as always, we like to hear your feedback. So please check in with us on Twitter, Facebook, or LinkedIn. Don't forget to sign up to our daily or bi-weekly newsletters. And thank you very much for your interest today. Thank you, Markus, and thank you, Michael, for this exciting talk. And thanks again to the entire team behind the scenes for doing this great job week by week again. I hope you all will stay safe and stay healthy. And thanks for joining us. I hope to see you later today or in the next weeks. In the meantime, visit our website or follow us on social media. Thank you and bye-bye, guys.